The cradle, we decided to design solar panels inspired by butterfly wings and photosynthesis. The majority of solar panels today are made from silicon. Silicon can be extracted from sand all over the globe and is used to make the actual photovoltaic cells and the photoresistors. Then a layer of ethylene vinyl acetate is placed directly above the solar cells to act as a protective barrier when the tempered glass is pressed on. This tempered glass is strong enough to protect the solar cells from hail damage or other extreme weather conditions. A lightweight aluminum frame is used to hold all of these components together. Polyvinyl fluoride is used on the underside of the solar panel to provide physical protection and insulation. Lastly, the motor attached will be composed of iron and copper.
Next, we have how a raw material is acquired. First, we have sand. This material is mined mainly from sand pits, beaches, oceans, or riverbeds using shovels. Next, we have glass. Glass comes from smelting together sand, limestone, and soda ash at high temperatures. Once the glass is cooled, it turns into a solid form. Third, we have aluminum. Aluminum is obtained from the ore bauxite. Bauxite is refined, producing aluminum oxide. The aluminum oxide is then smelted to obtain pure aluminum. Next, we have ethylene vinyl acetate, or EVA. EVA is produced from combining ethylene and vinyl acetate in a high-pressure reactor, allowing them to bond into the EVA compound. Then we have the polyvinyl fluoride, PVF. PVF is created by the polymerization process of vinyl fluoride with the use of catalysts. These materials are placed in high-pressure conditions in order to form PVF. Next, we have iron. Iron is made from heating up an iron ore in a blast furnace. Iron ore can be found from mining deep under the earth. Last, we have copper. Copper is found from the mining of copper ore and refining or separating the copper from the unwanted materials.
The impacts of these raw materials on the environment. Sand excavation affects rivers by sucking too much sediment out of them, which contributes to bank erosion, shrinking of rivers, and sinking deltas. Sand extraction increases flooding and also the lowering of water levels, which in turn harms marine life. The only downside to glass production is that during its melting process of raw materials, CO2, a greenhouse gas, is emitted from the fuels used for energy in the actual melting process. In order to collect aluminum, large plots of land must be stripped down from the vegetation, which can lead to a loss of biodiversity, habitat loss, erosion, and carbon emission, which contributes to greenhouse gases. Ethylene vinyl acetate is not biodegradable, but since it's insoluble in water, it's pretty much inert and causes no harm to aquatic organisms. Polyvinyl fluoride imparts minimal environmental impact during its production process. It is also fire resistant, decreasing solar burden, and is no longer lasting, increasing the product's lifespan. Iron extraction is harmful for the environment from the giant holes formed in the ground that disturbs habitats. It also releases pollutants into the atmosphere. Copper mining has significant impact on drinking water, aquifers, and contamination of habitats.
Energy and chemical processes. There are several processes that go along with those before getting to manufacture. Verification processes involve combining hydrochloric acid with metallurgical grade silicon to turn it into trichlorosilane. Hydrofluoric acid cleans the wafers, removes damage from sewing, and texture the surface to a better collecting light. The semi-conductive silicon discs are coated with titanium dioxide, making them less reflective, limiting risk for aircraft. The silicon discs are arranged in a aluminum frame and silicon rubber or butyl plastic which protect each cell. There are several impacts due to those processes. Hydrofluoric acid is highly corrosive liquid that can destroy human tissue or decalcify bones. Solving silicon into discs for use creates silicon dust called curves with up to 50% waste and curves are nailed by workers and causing severe respiratory problems. Silicon gas can be highly explosive and it is known to be spontaneous combust. Sulfur hexafluoride is used to clean silicon production reactors, which can react with other chemicals to produce sulfuric dioxide, which is responsible for acid rain. How are the material disposed of? Sand. Sand will be disposed of with glass since sand is used to make glass. Aluminum can be recycled for solar panels or other products. It can be recycled infinitely time, which will help the footprint of solar panels because they can reuse the aluminum they already have as many times as need. Ethylene vinyl acetone. Ethylene vinyl acetone is not recycled like other materials. It will end up in a landfill. It can be recycled for use in other solar panels and products. The excess that is made during production can be used in next batch rather than throw away. Polyphenol fluoride. Polyphenol fluoride is considered recyclable, but it is not recycled due to what it is used to. It is used for. It is used for fire protection, and that is why it is tossed out rather than recycled. Iron product can be taken to repair shop to be disassembled or can be recycled by melting it and creating a product. Copper. Copper is highly recyclable because it preserves 90% of its original value and it is easier to recycle than to mine new copper. It can be turned into wiring or it can be used to form alloys when mixed with other waste metal.
I'm Pablo, and I'm basically going to talk about the integration of cradle to cradle into our design. To integrate cradle to cradle into our design, we decided that we needed different kinds of solar panels. We couldn't use the silicone ones because they're extremely bad for the environment. They create a lot of pollution. They reflect a lot of heat, creating like hotspots that can actually kill birds and insects. And so we decided to use this new type of solar cells called dye-sensitized solar cells that use organic materials that are in the atmosphere and also organic materials like mangosteen peel that can be used as the electrode of the solar cell, and biocarbon from a brewery waste, which is going to be spent grains that will actually activate that electrode. And so basically we're using the waste from other industries into are designed so that none of it gets wasted and put into a landfill. We also needed a frame for our design. The frame is going to be made out of hemp plastic. The hemp plastic is non-toxic. It's a lot better for the environment. It's biodegradable, and also because of the heat that needs to be absorbed, is fire retardant and has high durability. So that's what made it good for our design. And basically, our design is going to be a solar panel made out of this dye-sensitized solar cells with 4 motors underneath, which will be powered by other solar cells that are also dye-sensitized. And whenever light from the sun strikes those solar cells, the motors will know where to turn to pose the big solar cell into the sun. Also, we thought about how solar cells right now reflect a lot of heat and light into the environment and is bad for insects and birds. So we saw that we mimicked the design of butterfly wings that don't have pigments, but instead have a specific structure of scales that absorb the light and don't let any light through. That's it for this slide. For the waste of our product, the only waste that we have is the hemp plastic, which can actually become compost when its lifetime is done. And the dye-sensitized titanium oxide, the dye of the oxide is actually made out of mangosteen peel, like this type of oil. So it can actually be used it's an organic material, so it can actually be used for compost as well. And the titanium oxide actually can be reused and doesn't lose any of its value or any of its components during its lifetime, so it can be reused into making more solar cells or making paint and stuff like that. And this is the biological and technical cycles. So basically you have the mangosteen being cultivated and the peel not being really used, so it's being given to us. And the grains from the breweries, also the spent grain not being used, so we can make into the solar cells when combined to the titanium dioxide. And from that, there's really the only waste that there is the hemp plastic that becomes biodegradable, the spent grain biocarbon, and that's also biodegradable, and the mangosteen dye that is needed to make the photovoltaic cells is also biodegradable, so it can really go into compost to make more mangosteen and more grains to keep the chain going. And the technical cycle, titanium dioxide is actually really recyclable and doesn't lose any of its value, so we can just use from other titanium dioxide from other industries like paint industries, battery industries. They use a lot of this and eventually don't need it anymore because it loses those capabilities, but it's actually still usable for our project. And again, the assembly goes in, the titanium dioxide pigment goes in to be coated by the mangosteen peel electrode and then activated by the spent grain material to make the photovoltaic cell. And again, there's not really any waste since the titanium pigment does not degrade. The only thing that degrades is really the organic materials that can go back into the environment and make compost, and the titanium pigment can really just be used for anything from sunscreen, paint, or again, solar cells.